computers, unorganized computers. The thing behind me, if you haven't seen it, is the SAVE, the semi-automatic ground environment, which we're scheduling and talk for in the near future, so stay tuned for that. Most of you know what we're about. This is the Computer Museum History Center. We started with a collection from the Computer Museum in Boston, and we're establishing a West Coast outlet, and eventually going to open a public museum. Right now you're in a private museum. It's a visible storage warehouse. And sorry for the difficulty in getting through the front gate. We're here through the auspices of NASA, and we're very grateful for their support. If you'd like to make it easier for yourself to get through the front gate, one way to do that is to become a member of the Computer History Center. What we're really trying to do is encourage people to become founding members. And the price is steep. It costs you $1,000 to do that. But if this History Center is going to be a success, it's only going to happen because the people in the industry support it. So we really encourage you to do that. The closing window for becoming a founding member is the end of June. And in subsequent years, if you don't see yourself on the founding member list of the Computer History Center, you may come to regret it. So now's the chance. On the other hand, I should also point out in fairness that if you want to become an ordinary member of the Computer History Center, there are sign-up sheets in the back. That only costs you $50, and it still gets you the badge that gets you through the front gate with a lot less hassle than if you don't do it. So any way you can, please support us, and eventually we'll become a real museum. You have a great talk tonight, and I'm going to turn it over to Peter to introduce us.
I'm Peter Bergson. I work with the Bay Area Computer History Perspectives, and that's a group of myself and Jimmy Trico, also from Sun Microsystems, who will be holding these talks with ourselves, more recently with the Computer Museum as well, on computer history topics for now 5 years. I look around, and of course there's George Michael here, and Norm Hardy and Barbara Costello, who were all here at the very first talk, which was also about Livermore. The first talk that was back in 1993 was on 1 year in the history of Livermore, 1963. Now the speakers tonight have undertaken to cover 20 years of Livermore history in one talk tonight. So we'll see if they can. We need to wind up around 7:30. If we haven't finished by then, we may well have another program. Possible. But don't feel you're cut short if we end at 7:30. You might just continue on another day. I'd like to say that we had a program like in January on operating systems and networking at Livermore, and this program now on hardware at Livermore. And you'll have seen in the announcements for the program how we, the staff of the Computer History Center and Bay Area Computer History Perspectives, express our gratitude to George Michael for his work in arranging these programs. And George has been not only arranging these programs, but working full-time, I would say, to conserve the history of computers at Livermore, including computer graphics, where George first worked at Livermore. And so we got tired of just expressing our gratitude, so we want to express our gratitude in a more tangible way. George, can you come up? You're unprepared, I see. Come on up.
You're on, George.
And what I got here, no fancy gift wrap. We figured you're a plain spoken man, so no gift wrap.
Why? This is terrible.
This is terrible, he says. We shouldn't do it, he says. Too late, the die is cast.
Too late, the die is cast.
It's a plaque here. And it says, I'll read it, presented to George Michael by the Bay Area Computer History Perspectives and the Computer Museum History Center in recognition of his contributions to preserving computer history. Moffett Field, March 31st, 1998.
Thank you.
Okay. Well, thank you, George, especially for the last two programs and the program tonight, and your continuing work in Livermore. Thank you.
I'll keep it up with that. They're black.
Okay, so I'll now turn it over to our speakers, and Ed LaFranchi in particular, who will introduce everybody else. I don't know. But you need to pass around. Don't turn it off.
Well, let's see if my colleagues will come up here. I'll get to them in a minute. But first of all, I'm going to get settled here. This illustrious group that dates from 53 to the present has decided that they would like to dedicate this session to Sid Fernbach. We believe that Sid and Fernback vision and leadership drove the hardware aspects of the computer industry in this country and in some sense throughout the world. Sid had a great rapport with the Atomic Energy Commission at that time, so he was able to get money when perhaps other people couldn't. But he also had a great relationship with the computer people, and he was able to get their attention and deliver the things that Sid thought needed to be done. So to Sid, we say, thanks, Sid, for all the stuff you did for us. I don't know how many of you are familiar with the now called E.O. Lawrence Livermore National Laboratory, but back in 1952 it was called UCRL, or the University of California Radiation Laboratory. It was founded in 1952 by Ernest Lawrence and Edward Teller as the nation's second nuclear weapons laboratory. There was a contingent who transferred from what's now the Lawrence Berkeley Laboratory. There were 50 people who came to Livermore at that time to start that. And one of those people who came to Livermore at that time was Cecilia Larson. She was one of the first people employed at Livermore and the first female employee at Livermore. I'm going to get back to Cecilia in a minute, but over the years the laboratory has grown from 52 people to some 9,000 people today. It is now a multi-program laboratory funded by the Department of Energy, and it has gone through all of the machinations of growing from what really was a scientific laboratory into very large billion-dollar-a-year operations. So it has some of the problems associated with management and administration, and God knows bureaucracy, particularly from the outside. But it is now different, and there's still an employee on the laboratory who's on our staff, Dave Pearson. So let me get back to introducing the people. Cecilia was the first one who came to Livermore. She was part of the original team that went to Philadelphia to learn how to use and program on Univac 1. She went with Lou Milfrey, Chet Kenrich, Dick Harpin, Ray Telesky, Ralph Thompson. I think that was kind of the crew. They were there for about during the winter of 1952, and the machine was delivered on or about April 1, 1953. The second person to arrive in Livermore was myself. I had started in Berkeley. I took a couple of years out to serve our Uncle Sam during the Korean War. Came to Livermore in November. In fact, the date was November the 17th, 1953, and that's when I first met Cecilia. We too were working on the Univac. The next person to arrive in Livermore came as basically a contract employee. He came with Univac when they delivered Lark number 1, and that's Chuck Cole. He was employed by Remington Rand Univac. He came out as part of the installation and checkout crew, returned to Philadelphia, and went then to the David Taylor Model Basin to install Lark number 2. Returned to Livermore and became a Livermore employee in 1963. The next one to arrive, sort of between the time Chuck was there and after, is Bob Wyman. Bob came to the laboratory from Northrop, actually Nortronics, in 1961. And the last of the panel to arrive was Dave Pearson, coming to us from Bell Laboratories in 1965. So that's kind of who we are. That's where we came from. We cover a long span of time with the computer business at Livermore. You have, or should have now, handouts. Did we just pass out the handouts? We had made some view graphs, but technology being what it is, there's no view graph machine there.
So pass the handouts from this side down to that side. At the end, if you have extra handouts, just pass them straight to the back. And if you happen to know the person sitting next to you, you could share a handout with you.
I just want to tell you our general plan tonight is that Bob Wyman has put together sort of a history of technology, at least an early history of technology, because technology is what actually drove the computer industry early on. It was the development of new technology that made new machines available. And Bob has done that. And once he's finished with that, we'll then kind of go back to square one, which is Univac 1, and kind of begin our informal stories about what happened. I see a number of faces here of people who either used to work at the lab or still work at the lab, and so it's going to be difficult for us to lie about a lot of stuff. But we're going to try.
But we're gonna lie anyway.
Okay, Bob, if you want to get started.
Can you hear this? Is this going to talk okay? The laboratory had, over the years, one-off of all the technologies as they came along. Now you have to remember that the first electronic computer here in the U.S. was the ENIAC, which was a wired program machine installed at the Ballistic Research Laboratory. And it was built by Eckert and Mauchly at the Moore School of Electrical Engineering under contract to the government. It was effectively the implementation of desk calculator hardware using electronics. So it was a lot faster, but if you looked at it carefully, you saw all the wheels and all the indicators and all the stuff that goes with making a desk calculator. Well, about that time, von Neumann had come up with the model of the so-called von Neumann machine, which was the sort of the standard model for a number of years. And Eckert and Mauchly saw the handwriting on the wall, and so they made their second machine, which was the EDVAC, as a stored program machine. Now, the thing that drove computer design at that time, people pretty much had the electronics under control, but what they didn't have was memories under control. Memories were very chaotic. The EDVAC used a mercury tank delay line memory. They had a bunch of these mercury tanks which had piezoelectric crystals at each end, and they would launch bits into these tanks, which would then drift from one end to the other, be picked up by the piezoelectric crystal, reshaped and rewritten. So these were just circulating delay line type memories. The EDVAC was a kind of an interesting machine. It was a 4-address machine with 16 instructions, and the 4th address was used primarily for optimizing programming. Now the EDVAC technology was carried over by Eckert and Mauchly into Univac 1. The Univac 1, which came to the laboratory, had mercury tank delay line memory in it. And so, whereas it was the first commercial electronic computer that the laboratory bought, it was certainly not a world beater compared with what we've got today. Now, at that time, there was a lot of research going on into memories. A parallel memory was being developed at Illinois and used on the Iliac machines called the Williams tube memory. This was a memory which used a cathode ray tube, and the electronic beam would write a spot on the tube, which would then be a 1, and if they sampled that spot with a beam, they would detect whether or not the spot at the particular place was charged by how much current flowed in the beam at the time that the beam was launched. These memories required a lot of regenerating because the little spots on the target of the tube would slowly drift away. So there had to be a memory recycling time on all of these machines, which used that kind of technology. And the IBM 701 used the cathode, the Williams tube memory. Now, IBM was also working with MIT on the design and construction of core memories. And core memories, of course, finally came along and were an extremely useful and long-lived mechanism for recording data in the machines. Now, a couple of little anecdotes about the core memories. These were little ceramic cores. They were a ferrite ceramic core, and they would be suspended on wires in these tanks. In the original ones, they used a fluid, a transformer fluid to cool them. And there were cases where the little cores would actually spin on the wires and saw through the wires. Okay, this didn't happen often, but it was one of the little characteristics that these things had. Now, digital had an interesting problem in their memories. These were air-cooled memories, and they had these core planes which were all stacked up, and they had a fan blowing through the stack to keep it cool. Of course, we're very temperature sensitive, and the characteristics of the fan and the characteristics of the stack were such that there was a peculiar characteristic in this fan, and so there were two operating points, which made the whole thing unstable, and the airflow through the stack made the stack puff. And they didn't know that and the planes all just moved, and they didn't know that they had this problem. All they knew was that occasionally they'd break a wire. And so finally, one of the mechanical engineers there at the lab, at Digital ran a study on these things and discovered this peculiar characteristic. And Digital then, in their infinite wisdom, decided that the fix was simply to take the fans off the stacks and hope for the best. And it turned out that it worked. Okay. Well, anyway, this is essentially the technology part of the thing. The IBM 704, I believe, was the first core memory machine. The 701 was the Williams tube machine. The Univac 1 was the mercury tank delay line machine. And core memories then lasted for 15 or 20 years. As an aside, the IBM 7030, which was delivered to the laboratory in 1961, had a 72-bit memory. There was an 8-bit single error correcting code in this memory. But IBM got into a lot of trouble with the stretch, the 7030, in that they were having a hard time getting it delivered. And there was a lot of turmoil at the top of the organization because the 709, which was their then profitable machine, was becoming obsolete. And so they finally decided that what they would do was build a 709 copy using the stretch hardware, the stretch cards, the so-called York circuits, which were very fast and very reliable. And they also used the stretch memory. Now, the stretch memory being a 72-bit memory, and the 709 being a 36-bit machine, every time they took a memory cycle, they got 72 bits out, and they would just use 36 of the 72. And this was one of the things they did when they made the 7094, was they began, when they did an instruction fetch, they would save the second 36 bits and save actually one full memory cycle in the fetch. And they also jacked up the speed somewhat on that machine. Well, anyway, I've got kind of ahead of myself here. After the Univacs, the LARC was the machine to be delivered next, and Chuck will talk about the LARC.
Well, I don't know how many of you are familiar with the LARC machine that came from Univac in 1960. It was a machine that performed decimal arithmetic. It had 12 decimal digits. 5 bits were used to represent the decimal digit, and there were 12 decimal digit positions, and so the arithmetic was 12 times 12 in straight arithmetic. It also had floating point capability. They would strip off the 2 upper digits, and they would represent from 0 to 99 in a floating point. And so there was actually a computer, one computing unit. There were 2 processor units that drove a large array of drum disk or drum storage units. We calculated the storage capacity of one of those recently. Do you recall what that was?
Yeah, it was. I thought it was like a half million words.
Okay, so it was like about 500,000 words on one of the drums. So it was a fairly sizable storage capacity. The LARC, I mean for the day, the LARC also Well, they were huge drums, yeah. They were about 3 feet long and maybe about, I would say 2.5, 3 feet in diameter. And so they were quite large. There were 12 of them in the array that was delivered to Livermore.
Did they have fixed heads or flying heads?
They had flying heads. It was a flying head disc, a single head that traversed the disc in increments. I think there were 100 bands on a disc or a drum unit. And so, you know, it was modern technology. I mean, these heads flew most of the time. Let's see, I also want to point out that it was a fully transistorized machine, except for the drivers for the core memory. They still use vacuum tubes to drive the high current requirement to switch the cores. As I recall, there were 4 sets of 4K storage in a given unit. I think there were 2 memory units, as best I recall. So we had 32K of storage that is immediately accessible storage. Let's see, what else can I say about it? There were about 100 instructions, most of which were unique. Some of them were repetitive, but as was common in those days. You could do double precision arithmetic, and I guess that's about all I can think of.
Round holes in the cards?
I'm sorry?
Did it have round holes in the cards?
Yes, as a matter of fact, I believe so.
It had electronic page recorders too, which was very nice the first time.
Yeah, George mentions that there were electronic page recorders as a part of that system.
Had a cigarette lighter at the end of it.
That's true, it did, I forgot about that. Bob Crowley points out, I mean, there are people here in this audience who were there in those days as well. Points out that there was a cigarette lighter in the printer unit as well. I mean, it was, you know, it was like whoever designed
When
that.
smoking was okay.
That printer felt the need. Occasional break, yes.
Did Livermore drive the 12 decimal digits, or was that just an offering by the company?
That was an offspring of the Univac, that was a 12 decimal digit machine. It's just a
Right.
carryover from
Yeah,
that.
it was just the evolution of what was going on in Univac in those days.
So it's
Well, that may well be, I don't recall. The comment up here was that Sid didn't really care what it was binary decimal, just so it worked. And it worked reasonably well for 8 or 9 years.
About questions, it'd be good if you could repeat questions, because people are looking at the tape and not hear the questions.
Okay, thank you.
The core, I want to say something about the core memory drivers. They had this rather bizarre core memory system, core memory driver in the thing, which had a transformer in it, which had a one-turn secondary, which drove the cores, and they had this little power triode, which drove the primary of that transformer. Now, the transformer itself was a vapor phase cooling transformer. It had a fluid in it, which boiled during the clock pulse. And the transformer would run for several months or maybe several years, and then the transformer would die, and they'd open the case up, and all the fluid would be gone. And they could never figure out why this transformer case leaked the fluid away. Now, the transformer was a very difficult transformer to make. It was a wound core transformer. They had this special alloy, and they wound this core very carefully on the thing. And Remington Rand, at one point in the process, said, "We are no longer going to make this transformer for you." And we used 3 or 4 of those transformers a year. And so the laboratory said, well, okay, send us the specifications for the transformer, and we will find a bidder for making these transformers. We went out to bid on these transformers, and there was one company that replied, and they wanted something like $2,000 or $3,000 per core. And the Department of Energy contacted Univac and said, like it or not, you're going to make transformers for this operation until Univac the LARC is retired.
Thank you, Bob. As part of the handout, there are a number of photographs that don't turn out too well in black and white. We actually have these in color in one set that we've left for the museum. So those of you who are really interested in seeing some details in these photographs might find it interesting to look at the color side.
If you find this particular photo here, this one I'd like you to look at, because it has Sid Fernbach over on the left side there. This photo. This has Sid Fernbach over on the left side, who we, as Frankie mentioned earlier.
Number 14, yes.
Number 14. And that's Harold Brown in the middle, who became Secretary of Defense later on in life. And he was the director at the lab at that time. And on the right side, of course, is Edward Teller, who many of you also recognize. So that's a particularly interesting photo. In front of the Univac console, the Univac Lark console. Univac?
That's the Lark.
That's a Lark. That's the Lark, I think.
Yes.
Yeah, that's the Lark.
Cecilia would know.
That's the Lark.
I also want to point out, as part of your handouts, there are a couple of these histograms that we've included that start way back in 1953, which was with the delivery of Univac 1, and sort of chronicles the delivery of computers to the Livermore Lab and how long they were there. And so this is a fairly complete history of the high end of the computing equipment that arrived at Livermore.
Okay.
So where?
There's a question.
Oh, I'm sorry, question.
So what was the uptime of the computer?
So the question is, what was the uptime of the computer? Lark. The Lark system we're talking about. Let's see. That was about 30 years ago. I think we ran on the order of about 80%, 85%.
24 hours?
For 24 hours, yeah, it ran 24 hours a day, 7 days a week, just as all the computers at Livermore have historically. I might point out that there was an acceptance period that was required. One of the reasons I was at Livermore for a year with the delivery of that system, and by the way, the delivery team for that system was about 40 plus people, many of which, of course, were mechanically inclined and plumbers and, electricians and that sort of thing.
And how late was it?
It was delivered right on time. To the best of my recollection, it was delivered on time.
Chuck?
Yes.
I think we ought to recognize that it didn't run very well at all with the tapes that the Remington Rand delivered with it. And our own engineers installed IBM tapes on the thing, etc.
Sacrilege.
You got it.
I have no allegiance to you that way. George's comment. Did everybody hear George's comment? Did it come out on the tape? Okay, I won't repeat it then. I don't think it was worthy of repeating. But I was trying to point out, though, that the installation crew for the Lark computer was about 40 people. It was something more than 40. The bulk of which, probably 25 or so, were here about 3 months. That is, installing this gigantic set of hardware, which would probably have filled most of this room. In fact, with the drum system, it probably would have filled this entire room. And so most of the mechanical setup of that system took about 2 to 3 months. And then we started an operating window of time that included an acceptance period. And so we had to do, there were certain performance standards that were required, not that that's such a foreign concept, but back in those days, the performance standards were somewhat more difficult for us to achieve. And it took 11 months total for us to finally pass the acceptance test. And so I was here with a crew of 4 people for 11 months through that acceptance window. Then I went back, as was pointed out earlier, to Univac in Philadelphia, which was where I was based. We delivered the second of our computer to the Taylor model base, and we actually got through that acceptance window in 4 months, with the installation included. And so we had learned a lot of things after the experience with the first one. And then I came back to Livermore as part of a maintenance contract for the Lark, and that's how I happened to get up.
Well, can you quote a price? Because computing is so cheap now.
Does anybody remember sort of what we paid for that?
Oh, it's about $3 million.
$3 million. George was holding up 3 fingers. So the question was, what was the price tag of a Lark computer? And $3 million is probably not unreasonable. Yes.
Did Livermore usually buy these computers or is it?
No, we bought it.
No, those IBM machines were all leased. The other machines, the Univac machines, were purchased up through, I think all of the control data machines were purchased also. They're all purchased.
Yeah, I think it was only the IBM experience where we actually did leasing. everything else was purchased.
I'm almost certain that all the IBM machines were all, I don't know about the Stretch, but I know all the other 7,000 series machines were all leased machines, because that's one of the reasons they were leased, is you could turn that machine over as the new machine came available, you could just get rid of it right away, and you wouldn't have to go to Congress to get money to buy a new machine. So you could pay for it out of operating funds rather than capital funds.
Was there any salvage value to the other group? That's
Very little. If you purchase them, you mean, you purchase machines? No, usually not. On occasion, I think in later years with the control data machines, there was some turn-in value to them. But not in the early days.
The salvage value would have been in reclaiming the metal.
Yeah, gold. The Larks had $30,000, $40,000 worth of gold in it for gold plating of the piece
Now,
of
back in
gold.
those days, I'm not sure you could have recovered it for $30,000 or $40,000. I mean,
And you have no idea how hard it is for the government to sell anything to anybody.
Although we did manage to give away quite a nice collection. But it took a long time.
in the early days, IBM didn't sell machines to anybody.
That's right. You couldn't buy them.
Rob probably
That's
makes the
right.
point here that in the early days, IBM did not sell computers, they only leased them.
Although they may have had special arrangements for
No. If they did, they didn't with us. Okay, so are there any other questions on sort of the large experience?
One of the other anecdotes I remember, I arrived at the tail end of the Lark era, but these machines would require big motor generator sets for the power system. They had big 400 cycle motor generators that filled up substantial rooms themselves. They were regular power plants, and I don't remember what the total power consumed was, but I think the MGs were like 250 kilowatt each, and there were several of them, so maybe you remember, Chuck, the total power, but just the infrastructure to support one of these early computers was mightily impressive. And the air conditioning and all that shit. But the question that.
So would you work with the computer manufacturer to design the building ahead of time, the physical buildings, to have all those?
Oh yes, and to have it all laid out, the power distribution systems and the air handling systems and the heat exchangers for later with the CDC machines with the Freon, all of that. All of that had to be pre-set up. Yes.
Yeah, that's an interesting question about making the facility available, because in the early days, the computers were all sitting on concrete floors, reinforced concrete floors, and when the IBM machines came in order to get the cables from one module to another, you needed to cut holes in the concrete floor with a concrete saw. And literally, you had to do that. And of course, when you got rid of one machine and you bought another one, you had to go back and refill the holes and cut some new ones. And so the raised computer floor was an immense help, because it significantly cut down the cost and the time and kept your structural integrity in addition. Let's see.
With one comment about power, the Cray 1s, I believe, had a power supply which was 5 volts and 18,000 amperes.
You talk about the environmental aspects of machines. I want to go back to Univac 1 when it was delivered in 1953. There's only a few of us here who remember that. But believe it or not, it was an electronic machine with some 3,000-4,000 vacuum tubes in it, but it was cooled by a swamp cooler. And if you people know what a swamp cooler is, well, it ran for quite a while. Unfortunately, the maintenance people who were to change the filters and keep the dirt out of it didn't do a very good job. And after a while, we began on some really kind of hot days when it got to be pretty moist in there. We got some stray electrical circuits going and some shorts happening, and we finally had to shut the machine down and take all of the modules. They were modules that held 14 tubes on them, and you put them in with big screwdrivers and stuff. Had to take all of those out, wash them all off in alcohol, and reinstall all of them, and then try to restart a machine that had all these vacuum tubes in it. And And it turns out that that was a horrendous job, just bringing that machine back up again. Bob had mentioned that it used mercury delay lines, and it did. It had seven tanks in there. It was a 1,000-word machine. We thought that was a huge amount of memory, 1,000 words of 12 decimal digits each. On occasion, the mercury would leak out of the tanks. And so the safety people would come around and say, or we would call them and say, we have a mercury leak, and they'd say, yeah, you have, now you've got to clean it up. Well, no, we didn't know how to clean up a mercury leak, and today, I don't know what would happen in today's environment, but we got by that process okay. It was interesting also that in working in that machine in the wintertime, it was kind of nice because you could open the bay door and get your back up against those vacuum tubes and be nice and warm. It was also the only machine that I know of that you could open the door and walk inside. It actually had a safety chain in there because there was a whole bunch, of course, of transformers in there. It was a fairly lethal place to be if you weren't careful, so if you got hung up, you could pull the safety chain and dump the power.
We have two questions.
Yes.
Bob Crowley first, and then
Those early days you're talking about, the machine went down at 1 o'clock and you put bomb sprinklers on the roof.
Yes, we did, right.
Can you repeat that?
Well, I said when one of the IBM machines went down, in order to keep things cool and happy, lawn sprinklers were put on the roof for part of the air conditioning system. Believe me, the federal government was not very happy about putting air conditioning in for anything, certainly not for people, and not very much for machinery. George Michael had mentioned about the lousy tapes that had come with the LARP. Well, believe me, I think those tapes were vastly improved over the tapes we had on Univac because the servo mechanisms were controlled by fish line. And whenever you had a break in the fish line, one would have to restore those, and it was not an easy task to do that. The tapes read both backward and forward, read a full block of information both backward and forward, so the machine had to be capable of reading in both directions, had to do that. It was a metal tape, they were very heavy, it was a phosphor bronze tape coated with nickel. You'd get bad spots on it, so you'd have to take the tape, stretch it out, splice it together, cut holes in there so the photocells could skip over that piece of tape, and it was a really interesting thing to work on. One of the most difficult parts we had with that machine, incidentally, was the I/O, just basically the printout of that. The only thing we had for printing was a Remington Rand electric typewriter that had been modified with some solenoids on the bottom, and it typed a character at a time. And you can imagine, poor things just got beaten to death. Eventually, Remington Rand built a 600-line minute line printer, and that seemed to work fairly well. No, that did not have the cigarette lighter. One of the early non-computer things that we did there in relation to that didn't come from the computer industry was we tried to build an interface and a unit to run Benson Lerner plotter, a flatbed plotter off of tape generated by the machine. We were reminiscing earlier about what we used for that, and I think what they used for memory were relays, but I'm not certain of that. Later on, I built a tape-to-tape converter to convert from Univac tape to IBM tape format and backward, and I can't say that I was too proud of the results of that.
I used it. I loved it.
It was obviously a vacuum tube device, and you had to convert from 8-bit tape, 8-bit bytes to 7-bit bytes, return to zero recording and non-return to zero recording on the other one. And so it was a fun project to look back on.
Yes, do you have a question?
Yeah, just for reference, this is the same electromagnetically secure building kind of next to 111, sort of on the next to East Avenue?
No.
Different building?
No, the LARC was not in that building. It's in a building that still is in use at the laboratory. It's actually, for those of you familiar with the lab, it was in building what is now 117. It wasn't called that in those days. The building you're referring to, of course, is what the big computer center is now. That's not
that was built.
That was built in '64.
The Univac building 100 was built in 1950, late 52, early 53, because it was ready when the Univac arrived. So. And it's still in use as far as I know.
I wanted to make two comments. One about the magnetic tape. The metal tape, and somewhere in this vast archive, there are copies. I mean, there are reels of that metal tape. So I don't know if they're on display or not. Someone perhaps associated with the museum can find that out. But they were kind of interesting, and they probably weighed, I don't know, 7 or 8 or 10 pounds or something, and they were really quite heavy. And it was 2,000 inches of metal, and so it was pretty heavy. The other thing I wanted to point out about the lark that was pretty fascinating too was that we would have open house at Christmas time and play beautiful music. I don't know if Bob or if any of you were involved in programming. Or maybe Norm did some of that back in those days on Hardy, but actually we played some beautiful Christmas music on the lark computer. Maybe that was his greatest claim. The lark was retired, I think it was in 1968, 68 or 69. It is in the handout that shows it on the histogram. So.
In the early 60s, 61 or so, Univac was experimenting with thin film and little cores. Did that ever get over the lark?
No, the question was in the early 60s, Univac was experimenting with thin film memories. No, that was never a part of the lark computer. In fact, I don't remember the first system in Univac. I left Univac at that time, so I didn't track them much after that.
The general registers were hand-wound cores, as I recall.
In the lark computer you're talking about, Norm mentioned that the general registers were hand-wound cores. And while I don't recall that, it's at my age, I'm just thankful that I remember that years. No, I'm a recent retiree, so it's not an excuse.
As long as we're on the lark, I have another anecdote. I ride there, like you said, near the end of Lake of the Lark, but it had these two drivers on the memories, but they were very it's a demanding application, so the tubes were swapped, the driver tubes were swapped out with great regularity. It turns out these were little external ceramic, I thought they were Petros, they're probably a little CX250 tube. And so for many years, about a decade, virtually all the ham radio amplifiers on the East Bay and the Valley ran these tubes that were swapped out that didn't quite pass muster on the large machine, but were just fine in some application. They're basically scrap. Question, Hans?
Yeah, can we get back to the energy consumption for a second? You guys are talking about how much energy these machines picked up, but most of our machines were running productively 80, 90, 95% of the time. Nowadays, we have 8,000 PCs sitting there that we're feeding to keep the screensavers running. What's the relationship between the energy consumption of one system and the other approach?
Did you get all that on tape? Maybe that's good enough. That's good enough.
Thank you, Hans. That's a very good point.
Yeah. Let's see, where were we in history? We were up to the early IBM machines.
Yeah, we go up to the early IBM machines.
Pretty well covered
Somebody
stretch.
covered about any more Univac stuff. I think that's probably about the extent of that. It left in 1958, and the Univac left in 1958 or 59. Yeah, Univac 1, right. Yeah, and then there was a period of time with LARC, and mainly IBM machines until when, like, the middle 1960s, I guess, when control data machines began to arrive on the field. The 1604.
No, the 1964 when the 6600.
The 6600 arrived.
But we had some 3600s
Yeah,
before that, right? So they came in 62, 63 is when control data machines began to arrive.
That's right.
That's all on the histogram, by the way, if you're really interested in the evolution of that vintage.
And I was wandering around here just a little earlier. See, the first 6600 was at the top of this chart. The serial 1, which is the old G machine, is the one over in the corner here. And back in the corner, still has some logos on it. And if you go down to about the 5th row below that, you'll see a series of 7600s that arrived. The first one arrived in '69, and that was called the arm machine. And the arm machine, or at least portions of the arm machine, are also back here in this corner. So, and later some of the crane machines and so forth back here. So the actual hardware represented by those bars are some of the interesting machines back in the corner.
Let's see,
Go ahead, let's talk about them for
well,
maybe a
if
while.
you want to do that, I was going to suggest that what happened during the early years is the laboratory either bought a machine or leased it, and the Livermore people were primarily involved in keeping those machines running, doing some I/O kind of things on them. And then as control data began to get into the business, the laboratory got less and less involved in building machines or building those kinds of things, and the era of time sharing began to arrive. And there was great effort on the part of laboratory employees in building all of the things needed to tie big machines together. And that era began in probably like about 1961, 62 is when we began really to develop a lot of the in-house things that could not be purchased from the outside in the time-sharing mode. And I guess the 6600 is the first example of the machine that we were first tied onto.
You might mention that first concentration right off the 66.
Well, I think that was Bob's thing.
It was really Bob's project.
You see, when did the time clock come into being?
Oh, yes.
I forget the time.
That was, what do you call it, the Wyman clock, Bob?
One of Wyman's great mistakes, okay? There was the machines at the lab used stepping switch timers to maintain time a day. And these were read through and read into the machines in various ways. On the 7094s, the clocks, these stepping switch clocks, were read in through the printer input. I mean, IBM had all kinds of bizarre ways of getting data in and out of the machines. And so you'd stand there and the machine would be running away, and then all of a sudden the printer would start, only it wouldn't print anything. It would go through a couple of cycles, and that was the reading of the clock. Now, the problem with these mechanical clocks was that they were very unreliable, and they were a constant maintenance headache, and none of the machines were all running on the same time. They were all off by a few minutes from each other. And one of the things the computing department wanted to do was establish a standard time base for all of these machines. So I got a couple of time standards, which I bought two so that I'd have a mechanism for switching over between them in the event that one of the time standards stopped. And then biggest mistake I ever made, I wired all of these bits in parallel from these time standards using coaxial cable around to all of these machines with repeaters at each machine. Some sadist who was writing the subroutines for this thing wrote a subroutine to get the time, and he called it Wyman. So anytime you wanted the time, you called Wyman. Now, all the machines were running on this standard time base, which was now very good. I mean, it was within a few tenths of a second at all the machines. But in the process, well, it was always that way. Okay, what occurred was one of the things they had to do in the operating system was take care of the people who loaded the machine up with files and then went away and didn't do anything. And so if files got very old, they were flushed out, a few hours old, and all the files were flushed out of the system. One day the Wyman clock developed a flicker in one of the bits. Okay? And in an instant, all of the files on all of the machines were too old. Everything got flushed, and the whole thing came to standby because there was nothing left to run. So yes, there are these problems. But
one time.
yes. Well, I should have hired an engineer to make it more reliable. One of the stories I love to tell about the constant love-hate relationship that the lab had with IBM. One of the things the lab people wanted to do was put in an alarm so that when the machine went idle, they could wake up the operators, okay, on the graveyard shift. And there was a little light. There was a little light on the console that came on when the machine went idle. And so the lab went to the IBM people and said, we'd like to connect a couple of wires to this light and take it off and run it through an amplifier, and we will then ring a bell when that light comes on. And IBM said, I'm sorry, you can't do that. That'll void your contract, and we'll have to take the machines away from you. So the laboratory, in its infinite wisdom, put a photomultiplier to the and when the light came on, the photomultiplier saw it and rang the bell and woke the operator up. Next.
Tell the original teletype interface.
Oh, well, okay. The really original teletype interface, which Norman Harvey knows all about, and so does George Michael, consisted of was put onto the CDC 6600 on one of the PPUs. Now the PPU was a 12-bit output, and it was a parallel output. And so we took all of these 12 bits and we ran them into a current driver, which drove the lines to a teletype, and we also sensed the current in that line and put that into another register or something like that. Okay, and so we just had this bit which came out of the machine. And Norman then wrote a code which sampled this 12-bit word, and anytime it saw a bit go from idle to start, he would then start a counter, and he would sample the data, so that we had a 6600 PPU serving as a UART. Now, I don't know if you all know what a UART is, but it's a universal asynchronous receiver transmitter, which you can buy today on a chip, and it has all of this timing and all of this neat stuff incorporated into it. But we did it all with software and a teeny weeny bit of hardware. So we started time sharing with 12 teletypes running in this rather funny mode. Now, as we went along, we began to put more and more teletypes on this thing. Norman said that if handling teletypes in this way was going to cause a problem, we were in big trouble anyway. So he persisted in believing that we should continue doing this single-bit type UART with software. Okay, but then Norman left and cooler heads prevailed, and we ended up building teletype concentrators using PDP-8s, later PDP-11s, I guess, which would collect, I don't know whether they collected characters or lines, but
there were several generations. Bob described one of the PPU. Right after that, we began tying all these machines together. In fact, had a pair of PDP-6s, which was the forerunner of the PDP-10, which was a fairly unreliable machine, as it turned out. PDP-10 was very reliable, but we used the PDP-10 sort of as a switch, you would think today, as a large buffer switch. And then we hung off the PDP-6, several generations of teletype interfaces. The original version was kind of a version of a bit sampler. And then when the PDP-8s came out, which were quite a breakthrough because of the inexpensive machine, as you recall, we had one of the early ones. I remember one of my first projects was an early PDA was serial number 13. I see we have an old one back here, number 26. But 13 is around the building someplace. And we used a sampling scheme there with using the internal registers of the machine as well. So the interfaces were very inexpensive and assembled in the software in characters into lines, and then moved lines around to the host machines, to the CDC machines, which were the 67s, which were the workhorses. That was ultimately, there were several of those built, probably half a dozen at their peak, 8Ls I think at one point. And then eventually, when the integrated UARTs became available, they switched to UART-based machines connected to PDP-11s. And the character and the rates went all the way up to 30 characters per second. Fast forwarding, we had a brief era where we converted from teletypes, most of them were Model 33s, to using the TI Silent 700s, if you remember those, which are 30 character machines. We used those heavily for, I guess, a 3 or 4 year period. And after which we began moving to the early CRT terminal, dumb CRT terminals, so-called, the ones that were not particularly intelligent. And there's a story, you could tell a story about the startup on the telephone model?
The startup?
Startup, sure, you mean the Blue Jay startup?
Yeah, sure.
I'll let you do that.
I got two anecdotes, okay. One on the Model 33 teletype. We had something like 500 of them running in the laboratory towards the end. Now, every time we ordered a teletype or a set of teletypes, we got a complete 3-volume set of maintenance manuals. There was no way to not buy the manuals, so we had a room full of manuals, which were available to anybody who wanted them. But again, being a federal government facility, there was no way we could give them away to anybody. They had to be given away to a government entity, and so we just sat on them. Now, the teletypes, these Model 33 teletypes had a line shaft in them with just bronze bearings and permanently lubricated, so-called. And there was a real problem with the life of these line shafts. The claim was that in 1,000 hours the line shaft bearings would be gone. So we put a timer on the motor, which would shut the teletype down if no character showed up at the teletype or nobody hit a key for a certain period of time. And then, in order to wake the teletype up, the software people had to send a non-printing character before any message came through, and you could hear the machine, even if it was running, it would go ka-chunk, okay? Nothing would print, and then it would go off and print the line. And this was the startup character on that time. Now, it turns out that the line shafts were pretty good. I don't think we ever had to repair a line shaft in the years that we ran these teletypes, but boy did they get noisy. I mean, you could hear those line shafts grinding away in your sleep. Okay, they were wonderful.
Another memory I have, back on the early PDP-8, we call them teletype concentrators. They're what today we call terminal servers, basically. But John Fletcher was the person who wrote the code for those things. I remember when we first put them together, and he was here in January talking. We maybe talked about this, but these were PDP-8s had 4K 12-bit words, and we really stretched. We were trying to pack all the line buffers for 128 teletypes plus the software to operate it into this little 4K memory, and just wouldn't quite fit, even with John's exceeding ability to optimize every bit in the thing. So we finally had to buy an extended memory, which was a second 4K module. And most of you remember how expensive those things were. We paid like $20,000 for 4K words. So that's 4K by 12 bits. So memory has come down, what, 5 orders of magnitude. It was quite amazing, but I just marveled at John Fletcher's ability to pack to pack so much into that little tiny, tiny memory. As we did, I guess, all of our software actually then, because memory was so precious.
Memory on the 7030 was $1 a bit.
Memory was so precious that you didn't even put the 1900 portion of the 1900s. Familiar with that problem.
Yeah, why don't we go to bulk storage?
Either that or outline a little bit about the Octopus network and how it all the stuff that guys all did, tying all that business together. Now, the Octopus actually got its name because I think when George and Norman first conceived this thing, it was supposed to be only an 8-legged device with some central unit. It got to be much bigger than that.
There's a chart here I have to find.
Well, I think the whole concept, and one of the reasons the Octopus name was derived was because the concept was that there was sort of the head of this switch, the main switch that funneled data from one node to another. You know, the big worker machines and the storage units and the communications channels all set out at the end of the quote, tentacles. And the PDP-6s in the early days and ultimately the PDP-10s sort of formed the switching mechanism to allow that communications to take place. And so hence the Octopus name was derived. You know, the mass storage unit in those days was called Elephant, and we had an ID checker. What do you recall the name of the ID checker? Ostrich, yes, the ID checker was Ostrich, thank you. Norman goes back a long ways there.
Which mass storage unit was called Elephant?
Well, I mean, the concept of mass storage was called Elephant. It was the Elephant system. Yeah, we're going to talk about the bulk storage evolution that occurred in Livermore as soon as we get to it.
The chart I was looking for was actually later vintage, so I left it there. I thought we had a chart back there of the early Octopus system, which has been introduced.
Well, why don't you go to the bulk storage stuff, Dave?
Okay, but let's talk just a couple minutes, unless we finished, about the concept of Octopus. Did you cover that pretty well? Okay. I guess there were 2 or 3 objectives. It was early on realized that there were advantages to having the ability to share files. So one of the early motivations, and Norm was very much part of that, some of that early thinking, was the need to have a central file unit, a file server. Again, we didn't call them those things in those days, which led to a hierarchy of storage, which I guess we'll talk about the technology in a bit here. There was also the early realization that with multiple compute nodes, compute servers, cycle servers, which were the CDC machines, there was an advantage to be able to connect your terminals to a single place and then route it around. So those two motivations were, as well as output going the other way, of course, or going to printers, or film recorders and microfiche recorders. So those were the early motivations for trying to tie these things together and to support the big thrust of time sharing. Time sharing was supported on the early systems and through the Livermore system, which I think was talked about in January, I assume, when the other people were here. So we had quite an array of handmade channels. You had a lot to do with the early channel, Bob. Maybe you want to talk about that briefly?
There's not much to it. I'll talk about it, but there's not much to the channel. Being a good engineer, I decided to steal Control Data's interface on the 3600, and so I made essentially a copy of their 12-bit interface, which had a handshake on it, and it would drive a twisted pair almost indefinitely long, and it was a nice interface because it was asynchronous. And the longer you made the lines, the data rate just slowed down a little bit, but no timing problems occurred. The one thing I remember is having been gone for several years, and somebody telling me that this data channel, which I had named the line unit, they said, "Why did you name it that?" And I said, "Well, because it was driving lines, okay." But what happened was that I was talking to one of the guys, and he said, we haven't made any changes in the line units for the last 4 or 5 years because we've run out of space. There are no spare circuits, there are no spare slots for boards. They came and asked, could we do this? We did that last thing, and it ate up the last circuit, and that was the end of it. We then just didn't modify it beyond that. But we put an interface at the 7090s which simulated a magnetic tape unit, because that was the only way we could conveniently get in without disturbing the IBMers. They did not like to be disturbed. The 7030. How did we get in the 7030? Do you remember that? I don't remember.
I did the interface.
Yeah. Oh, okay. Tape.
People should have tape unit simulator. That was my first project.
Yeah. Okay.
Next. Question. We have a question.
So what was the nature of the control in the center, the very first unit that you built? Was that was a PP6?
Yes, that was
from day one.
That was a PP6 pair. A pair of them. What they built, 13 or 14?
20 total. Each
20
one
total.
and tuned. They were terrible.
And so it was necessary to have two to have one running most of the time. One of the things we didn't try to describe was we used the early deck hardware, the early deck modules. If you remember some of you remember the old system modules, the preceded flip chip. And that was the early product that DEC produced before they really even started producing computers. And so the premium of making these hardware interfaces so simple was driven by of course the cost of those modules. A module that had 3 or 4 gates, you remember, those in the order of $100 in those days was a significant cost.
All germanium.
All germanium, and the 6000 series system modules, which were used in the PDP-6, largely used in the PDP-6, they just pressed the circuit technology very hard, and it was running sort of at the edge most of the time, which affected the reliability of the machine. The architecture was a wonderful architecture, and when they finally re-implemented it with the flip chip modules and as the PD10 series, it became just a real workhorse machine. Yeah, go ahead, and I want to go back to something.
The problem with the PDP-6, if you'll remember, the digital hardware philosophy was that you stack transistors, okay? You connected emitters to collectors and emitters to ground, and the bases were inputs, and when you had all the bases turned on, then this string would turn on and the collector at the top would go down, and so you built gates by stacking transistors. You could stack them 3 high. Now and those were germanium transistors, so the offset voltage was relatively small. Saturation voltage was around 200 millivolts. When they went to the PDP-6, they were using all silicon transistors because they thought for some reason or the silicon transistors was more reliable. But they kept with the stacked transistor idea. Now the saturation voltage on a saturated silicon transistor was about 800 millivolts. So so they restricted the stacking to 2 high. But that was 1.6 volts, which was getting right into the noise level of the circuits. And that is the ultimate reason why the PDP-6 was such a bad machine.
Reliability was. One of the systems we put together, kind of pioneered in the terminal area, we went past when we were focusing on just the alphanumeric terminals. But during the era we had teletypes, we did some very early work with the digital displays. We developed a thing called a television monitor display system, and we used some very early discs that were from a small company named Data Disk. Some of you might remember that pioneered very close flying, had very high density technology. And with a gentleman named Bob Swenson, who worked at the laboratory at that point, was the engineer that did most of this very early work, developed a scheme to actually record a TV frame in standard TV format, or nearly standard format, as one track on a disc. And so with one of these fixed head discs that had like 32 heads on it and worked most of the time, when on a good day you could lay down 32 tracks, 32 images that you could then read out and use to refresh a set of monitors. And so we built that up, hand-built that. As the discs improved, we built 2 or 3 more systems that actually worked somewhat reliably as the hardware stabilized. And then we replaced that early days of the RAM memories with early DRAMs. Yes. Okay. Chuck, remind me, I glossed over it. These things were driven from the central disk by a cable, good-sized cable. I guess it was RG 58 or 9, 58 big stuff. All around out to the laboratories, to sit adjacent to the teletype terminal, so you could sit there with the teletype terminal and then have actually a rather sophisticated graphic display available for that day. One of the more impressive sights I recall was the cable bundle that went out, because at one point this grew to about 500 channels of refresh, and this went through, and then it went through a digital switch, which was effectively a silicone version of a telephone office, and switched this out to a couple thousand more monitors out there. And so coming out of the switch, you can imagine a bundle of about 2,000 of these big coaxes all kind of just filling up the ductwork of the entire laboratory. It was I'm sure whatever we saved in local terminals we spent in coax. And it was a wonderful system that survived, I guess, well into the 80s, probably the mid-80s.
But for just eating up coax, the Wyman clock was the best.
So that was kind of the end of the I guess that terminal era until we converted to the intelligent terminals we all use today. Is this a good time to switch to storage?
Yeah, I think so.
Who wants to start?
Go ahead.
Let's see, I guess a product of the Octopus concept was that all of the computers should share some very large storage capacity. And so we embarked on a whole series of technologies and hardware that would support that concept. And so very early on we had a very large disk system, a single unit disk system with fixed heads. I think on page 18, or at the bottom of page 18, there's some reference to it. And you will note that in the last sentence of that, we say the system stores some large number of 12-bit words. Mainly because none of us could remember how many 12-bit words it actually stored. But it was, in fact, a central mass storage capability, or fast storage capability, let me put it that way, for all of the systems that were attached to the Octopus in those days. And it was still in the days of the CDC machines, 7600s at that point in time. On the next page, you'll see that there's some reference to the IBM data cell. There's an example of the data cell technology here in the museum. It used magnetic strips. They were about 12, 14 inches long, I suppose. There was a very unique system for retrieving one of those mylar strips. They were housed in a canister. I think there was something like a dozen canisters or 10 or whatever the number was, and I think there was like 20 of these strips in each of the canisters, and then there was an air blast. I mean, it would position itself to pick up one of those magnetic strips. There was an air blast that would separate the strips, and then there would, a tiny set of fingers would go down and pick up the strip and take it off to the read station. Okay, and then wrap it around the drum for recording and reading. And since it was magnetic, of course, it was reusable.
That was the easy part. Putting it back in was the hard part.
Well, no, it was done in the same way, of course. You know, you would position this thing and... No, for the most part, this worked very well, you know. The blast of air would open the hole, and you would drop this strip into the place where it belonged. And most of the time it worked. As noted here on our handout, the system actually stored 200 of these magnetic strips online, and of course we had an offline storage capacity as well. that the operator would manage. And each of the strips had 100 cracks, so the math is there for you. Let's see.
I want to go back on the disk. The data cell is 3 times 10 to the 9th. This big disk we were talking about was probably about 10 to the 8th. It was certainly down in hierarchy by more than order of magnitude. This was a disk that set disks that were 4 or 5 foot diameter, probably spun at 1200 RPM at best. So that was, in bytes, that's on the order of 10 megabyte, which is, and this was a huge machine. We probably paid $1 million or more for it. So this technology's come a long way also.
Yeah, some of those disks, the big early disks, had hydraulic head moving systems. And the hydraulic oil would be at 900 psi inside the systems, and every so often they'd break a hose in there, okay, and just spray hydraulic oil all over the disks. Somehow or other, they always managed to recover the data. They clean them up, they put the hydraulic hosing back in, they fill it up and bleed it and turn it on, and it would work.
The third level of that system put the disk data cell, and the third level was the IBM photostore, which was an incredible device, incredible system. Many of you have seen it probably, but this, for those of you who haven't, the storage mechanism was the cartridges about this high, about that wide and thinner, that held some fair number of pieces of film. I guess there was probably 20 or 30 pieces of film. 32. Okay. Some of the numbers exactly. And the
one cartridge, Dave, was equivalent to an 800 BPI tape.
Okay. A cartridge was an 800 BPI tape. George reminds me. I think the details. So anyway, the PDP-6 system was used as a buffer to collect. Oh, here's one. We do have some. Why don't you hold that up, Bob? There's
the box.
There's the box. The lid flips up, and there's one of the films. And so the PDP-6 would buffer up the data and send it out to this machine where it would get recorded raster style on the film.
Pardon? Yeah.
And then the piece of film would get sucked into a vacuum chamber. Actually, got sucked into the vacuum chamber for recording. And then it would go through an automatic wet film processing where the film would be further developed with chemicals and all developer and fixer and so forth. And if everything worked out, you would get good contrast ratio, and then be dried out and be dropped out and stuffed in this box. And there were some huge number of boxes. Several thousand. 7,700. George says, "What a memory!" And
he's making it up.
We're lined up in an egg crate and for storage. And this was an incredible volume. 10 to 12 bits was an incredible storage volume for the laboratory, which I guess it took 3 or 4 years of initial use before we filled it up the first time. After which the boxes would migrate into the tape library onto the shelves alongside the tape archives. The inverse to read it, robot arm would have to go fetch the cartridge, bring it over, open the lid, find the right chip, and pull it out. One of the more remarkable things I think that was done in support of this was the file management system that some of our PDP-6 software people put together. Garrett Gore, Clarence Badger, John Fletcher, the three of the names I especially remember, that did a remarkable job of by even modern standards, a very sophisticated file management system.
One thing about the recording process is that there were cartridges in the system which had unexposed film in it. And when they were going to expose the film, they used an electron beam. So the film had to go from ordinary air into a vacuum chamber where the beam could expose it. and it had to go through 1 or 2 outgassing chambers in order to to maintain the vacuum in the chamber where the recording went on. This was not a trivial system.
Yes. The photo store had a
Question.
Oh, we have a question?
Curious what kind of collaborations there might have been, discussions with IBM about specs and capacity of the photo store before you actually went ahead and got it.
Well, I think George probably could answer that better, but let me try, okay? We contacted, actually the project engineer for IBM was a fellow by the name of Jack Keeler. Many of you may recall that he rose to significantly high levels in the IBM corporation until IBM got into some financial difficulty, and then he and his friend lost their jobs, I guess. But we made contact with him about large storage systems and worked with him to basically develop the concept of this system. But everything, all the design work and everything was really done at IBM Saint-Zé's, where it was produced there on North 1st Street office, as I recall, in Saint-Zé. And we worked with them, trying to tell them, what our needs were, and the principal need was storage for 10 to the 12 bits of data. And I think that was kind of the goal that they shot for, and how to do that. And we worked with them on interfaces and how to do that. But basically the design, all of the film processing and everything else, design was done by IBM.
One other thing though, this wasn't a technology that was, when we requested it, IBM had quite a bit of experience in this technology because they were working on a machine for the NSA, which they absolutely would not talk to us about at all. But it was a film storage mechanism similar to this one.
This turned out to be the last photo store that remained in operation. It ran for a long time. I don't put the date down, but it must have run into the late 80s.
Turned off in 79.
79?
Was it? No.
Oh, no, longer than that, George.
It started in 69 and ran solidly for 10 years. Had to shut it off because they couldn't maintain it.
I guess we have mixed memory on that. The reason it was kept online after more modern equipment came on board was we had such an incredible amount of data stored on this, and since it was incompatible with anything else, the only way to be able to read the data was to keep it running. So we had a wonderful field engineer named Jim Dimmick from IBM who came out with a system, and must have been the laboratory effort of 20 years. And he ultimately retired when the photo store was shut down. But, I think that's right. We had to shut it down. Jim Dimmick retired, that's right. But,
He came with the 701.
He came with the 701, and because of Jim, and Jim, I still see Jim every now and then in town, and because of Jim, we were able to keep this wonderful machine operating far beyond anyone ever thought it could operate. It was eventually supplemented by a CDC tape cartridge machine, which is in the back of the room here, which had little tape cartridges about this long, about this big square. Each of those also held, that was a magnetic-based system, magnetic tape cartridge, fat tape, a couple inches wide. And each of those cartridges held also the equivalent agent PPI tape, and several thousand of those in an array. And that had a more limited lifetime because it came along somewhat later, but kept us in mass storage for a long time.
Anecdote, one of the great contributions of the Livermore engineers was to find a way to keep the film chips from sticking in the boxes. Remember, we had 50-gallon drums of surfactant down in the basement and pumped it up to wash the film off, make it dry right. That wasn't part of IBM's design, but it worked.
George had an important piece of history here too. Y'all heard that? I guess you got it on tape. Let's see what any other anecdotes. I guess we filled up the photo store several times.
1.1 times 10 to the 13th.
Oh, okay.
That's 11 times.
11 photo stores full. I remember 7 or 8, but that was I left before the end.
Yeah.
So that part. Maybe this is a good transition to then some. along with these large storage devices and large computers, we produce an immense amount of printout in those days, particularly in the early days of teletypes when you can relatively slow data links. Basically, the only way you get large amounts of data to the office was through printouts. And I'll let my colleagues talk about these wonderful machines, but I want to paint a picture for you. The typical office of Livermore is like a 10 by 12 office, a desk, and many offices, and Bob Crawley's amongst them, you would walk in and they would be stacked floor to ceiling, at least a third, maybe a half of the square footage on the floor to ceiling in stacks of this printout. That little, various vintages. So, let's see, who would like to start with some of the early printers?
I'll start the earliest one. I don't need one. Well, as I mentioned early on, the earliest printers were either electric typewriters or mechanical line printers. In the late 50s, there was a device out built by Stromberg Carlson in San Diego called the SC5000, and it was a marriage of a Kertron, basically electron tube, and haloid Xerox process. But what they sold was this device that if you put some characters in it, it would write it on a drum for you and print it out on a piece of paper, and it was roll input and roll output paper. Well, if you recall, even in the mechanical line printer era, people were accustomed to fan-fold paper, and it's kind of difficult to read from scrolls anyway. So the lab decided that they would buy this machine, but it fundamentally had no way of getting data into it and no way of handling the paper when it came out. So we took on the task of putting the system together, and what we wound up doing was buying a tape drive from Ampex Corporation, which goes back a long way. It was the first very high-speed digital tape drive that Ampex was building. They were very big in the analog tape business. I mean, that's where they eventually went on with the videotape recorders, and there's a little story about Ampex. But they built this device. It ran at 150 inch per second. Could handle IBM tapes. We built a control system out of modules made by a small company in Massachusetts called 3Cs. They were just little germanium transistor modules. And we bought a core buffer, a recirculating core buffer from somebody in Southern California. I can't remember the name of the company right now. But basically what we did is we'd read a block of, start by reading a page off of the tape and just running it through this recirculating buffer, because as a character came out of the buffer, it printed it. It registered on the drum. All the meantime, the paper is running, and at the end of the page, we have to stop the tape so you could get across basically the fan fold in the tape, because we converted this machine from roll input to fan fold, and I'll get back to that in a minute. So basically, we got this thing up and ran, and it ran fairly reliably. At least the part of it did. It had to go through it was a Xerox process, and so you had a toner in there, and the toner worked okay, but sometimes when you ran the toner and the paper through the fusing device, the paper would catch on fire. And sometimes the heating elements wouldn't come on, and programmers don't like to read paper where the toner is not fused. It gets a little messy. So we finally were able to change the elements, the heating elements. We actually went to some form of silver in there, and I remember that one of the guys was on the hook for about $15,000 worth of silver that had been checked out of the storage department. And then we built, with the aid of some clever mechanical guy, we built a fan folder. Well, periodically the fan folder would get out of sync with the folds in the fan fold paper, and so then you wound up with this big mess on the floor. But that system ran for a long, long period of time, and was fairly serviceable. I can remember Sid was very proud of that one time. Periodically, a group of the regents of the university, because we were all university employees and the laboratories run by the University of California, after all these many years still is, a group from subset of the regents would come out to see what was going on, to kind of give their blessing to this thing. And Steve asked me one night, afternoon, evening, I guess it was, would you come out and stand by the printer and make sure that this thing works for the regents, you know? Talk about this poor guy who was sweating it out with the regents there, you know? But it worked, it worked fine. And as I say, it ran for quite a period of time until we switched to another system.
I have a little anecdote with that from an operator point of view. We used to have to get up there with a mallet and whack on the toner bottle because the stuff was so fine. It would stick up there on the top of the bottle, and pretty soon nothing was coming out, so of course nothing was printing. The other thing that was always a challenge, besides the folding on the one end, is that we were taking it out. The boxes of fan-folded paper were in cartons, and we'd have to cut them open and tape them together so there was a continuous stream of paper, because you never ran out of this machine. If you did, you were in real hell, because you had to feed that through this machine, and of course the fire problem. So it kept you busy at both ends.
Yes, literally. I think that's the story of the SC5000.
One of the other real workhorses that we had at the laboratory for film output was a set of systems called FR80s. Who made those?
Information International.
Okay. Which were big, which were large CRT film-based systems, and because hauling cartloads of paper off the SC5000 right to radiation printer, which we'll talk about a little bit, filled up offices too fast. People gradually moved to film, and the microfiche of that era. So the FR80s were basically had solenoid step cameras and took pictures of alphanumeric CRT output. Now, at one point, we had 5 of these things running, and would produce formats all the way from 8 millimeter, 316, 35, 70, and fiche, and produce an enormous amount of frames. If you look on page 26, there's some data. These machines together produced about 12 million pages of output a month on film. And there were, during this period, there, in the basement of our computer building where these machines were located, we had quite a film processing operation. I guess at one point we were probably one of the largest consumers of film around, and we had all kinds of wash water. We used to wash down the drain, and we think today about the way we handled those chemicals. It's kind of scary. And it wasn't until the tail end of that, the use of these systems, that we actually began trying to recover the silver, recognize the value and process for recovering silver became known, or at least economic for us. There's a note here that I guess I don't remember this, but that we had a lot of camera problems. You beat the daylights out of these cameras, running them that hard, and they were even commercial grade cameras out for Hollywood film production. They weren't designed for this kind of duty, and so we beat them up pretty bad. And the first camera, were you part of that?
Well, I was there very late when the camera was in, and suddenly discovered that it was not light tight.
Okay, that was they watch.
It was a contract. It was a contract that they let, and they found a low bidder who would bid on this camera. We let. And the camera sort of worked. The big problem with these cameras is that it has to move one frame very quickly and register it properly, and then wait, okay, and then move another frame very precisely, and then wait. And it's not like a motion picture camera, which has got this thing running more or less at steady state. But in any case, the manufacturer of this camera knew about cameras reasonably well. But he made this magazine which just leaked light, and if it sat there for any length of time, all the film would become fog. And then there was a big stink, why did you make this thing not light tight? He says, where in the specs does it say it has to be light tight?
That's right.
You skipped the radiation.
Well, that's next to the
All
sequence
right.
here. That's a whole
So
story.
we left off our 80s because we were sick of the radiation.
Yeah. I wanted to make Hans will remember this story. We had quite an array of regular high-speed line printers, 1,000, 1,200 line printers around, both up on the mainframes as well as down the basement for a while. But those printers were pretty noisy. When they were going full tilt, 1,000 line a minute, 1,200 line a minute line printer could make quite a racket. And so as we started getting more and more heavily into time sharing in our Octopus network, and we're producing such large amounts of output locally as well, we began to get a little concerned about the effect on hearing for our operators. So we had a great little detour, Hans. Remember when we designed a sound cabinet? You remember the sound cabinet for the printer?
Yeah.
You don't remember that one. Ed does that. So we didn't know much about acoustics either.
Or anything else.
But we kind of learned quickly, and finally we learned the hard way that maths was how you reduce the noise, and we were able to put these ugly boxes over the line printers that ultimately allowed us to attenuate the noise to at least a tolerable level. But they were fiercely noisy machines, for those of you who remember those gadgets. So radiation printer, Ed, you want to start that?
Yes, I'll do the radiation printer. One of the reasons the radiation printer came along is that basically the SC5000 ran out of capacity, and online printers were really not quite the way to go. You really wanted an offline device so you could basically take the tapes off the machines and run them offline and get your printing done offline. And so we contracted with a company called Radiation Incorporated, and that's where the name Radiation Printer comes about. And we facetiously asked for something that would print 30,000 lines a minute, 500 lines a second. And this company, who had never been in the printer business before, in fact, they were an aerospace company, said, well, we can do that. and as it turns out, they did do that. What they did is they contracted with a paper manufacturer who built printing presses. And they bought a printing press and adapted it for basically computer printer use. Unfortunately, it used a form of paper that was insulating on one side and conductive on the back, so it was black on the back, and the way you form and just a single row of styli grouped in five-bit groups to form the characters, and as the paper went by, you fired the little styli correctly to form the character. Well, it was messy for a while. When they first built it, they thought there was going to be all of this debris built up on the styli, and so they put a system in where they used crushed walnut hulls to clean the styli to make sure that they wouldn't get all gunked up, and we found out that that didn't work very well. We got rid of that. In fact, we didn't need it. But
burn the styli out.
Burn the styli. It was really unnecessary. But as I say, they did build that. The electronics seemed to work okay. They forgot a couple of things, like they put part of the system over the oil drain hole, and the oil didn't get drained out for a year, and the transfer got gummed up. But it was capable of printing the three different tape densities at that time, which was 200, 556, and 800 dpi.
That's what the transmission's for, wasn't it?
Yes, that's right, to change the different paper speed. Paper came in big rolls. The rolls probably weighed at least a couple of 100 pounds. We had to get, how much were they?
600 pounds.
600 pounds. You had to get a forklift, a little forklift, portable forklift to pick them up. Our stores department didn't know how to handle these things when we first ordered them. It was interesting, but it ran until from 63, I think, or 64, until about 1972. 74. Was it 74? So it was a device that filled the need, although I think everyone was very happy to see it go, because it was a pretty messy output and pretty difficult to read.
7 pages a second.
Yeah, this stuff really ripped. It was like a newspaper coming off the printing press. The output, because it was burnt through this kind of grayish, light grayish layer on the black background. It was not very clean stuff, and if you worked with it very long, you'd come up your gray and black from the carbon in it. I don't know what it did to your printing apparatus, but we put an enormous amount through there. I think we printed on that thing like 3-4 million pages a month in production, year in, year out.
Yeah, I was going to add to that it started with a roll, then it had a knife on it, went through a knife blades to actually put the folds in the paper, punched holes in it because we needed to be able to put them together, so it punched holes in the top and the bottom, and then refolded it on the way out with a refolding mechanism. No, it was a screw type folder.
The fan folder, or the perforator, which is required for the fan folder, consists of a drum, 2 drums, one on the top and one on the bottom. And each drum has 1 anvil and 1 blade, and they're made so that when the anvil comes and meets the blade, it just meets it. Okay, and that way they perforate the paper right at that place. And they have to perforate it from one side and the other in order to make it fan fold nicely. Now the paper was slightly abrasive on the gray side. The back side was greasy carbon, okay, and so it was okay. But the side that came in contact with the rough gray side would always wear dramatically. They'd actually cut grooves in the anvil and wear the blades out so that they were round. And once the fan folder quit working, or once the perforator quit working, then the fan folder couldn't work anymore, and so paper would begin coming out in long sheets on this thing. So they finally went to tungsten carbide blades and anvils, and that cured the problem.
I remember as first coming to the laboratory, speaking of paper break, and this stuff would really spew out when it would break. If any of you have ever been to a paper plant and seen a paper break at the paper mill, it had much the same effect. This stuff would just spew out all over the place.
See, Dave, I'd like
Do you remember some more?
Just one more kind of offhand comment about that is because this paper was so messy on the back, we tried to get Crown Zellerbach Corporation interested in building paper that was basically a sandwich paper, and they worked pretty hard at it, but they finally threw up their hands and said there's just no way that they can build a paper to do this job. But I have to say thanks to Crown, because they really did try to work with us to get a paper that was going to be more acceptable.
Speaking of paper, since this was a special, basically one-off paper, it actually was pretty expensive. I don't remember the exact price, but compared to normal paper, it was a fairly pricey consumable because it was custom made just for this task. Unless there's more anecdotes on the radiation printer, that served a long and fateful life. But we then, as noted late in the notes here, went out and were able to procure a couple of xerographic process printers, which each printer ran somewhat slower. I guess we were on the order of a page a second. What did it?
Which is the Honeywell printer?
Yeah, Honeywell printers.
I think they were each of them about half the radiation.
You think they were half? Okay.
Because we got 2 of them.
Yeah, we got 2 of them, but I didn't. Okay. Anyway, these were xerographic printers, and kind of the first of the era of a number of printers. Later, IBM produced a printer like that, and I'm sure the manufacturers did also. So that was sort of the transition in the modern era. And the quality obtained at that point was just remarkable after having spent a decade or more looking at the output from the radiation printer. The 5x7 style, its character on a good day were a little fuzzy. And when the style became burned and didn't make the holes quite as crisp, they became really a marginal proposition to read. So the xerographic process was just, really appreciated by everyone at Livermore.
Comment about the Honeywell printers and the glue box.
Go ahead, Ed. Go ahead.
You guys know more about
I actually didn't work with those.
Well, okay. Well, maybe I was the only one around. We should ask Barbara, but this came out is cut paper. It actually cut the papers. I think it was cut paper. It didn't roll fed. And there was a cutter, and they'd stack it up. And so the way we distributed this, we actually the operators would swap, if it's a narrow bundle, they just dip it into hot glue. The real thing you tape it. There's a medium, a staple. But at a certain thickness, you bound it by dipping it into a hot glue bath, which is basically the glue that they used to bind paperbacks with. And this was kind of a not so neat process also, and it was smelly and hot. And I guess we used to glue up to what, 4 or 5 inches, Barbara? Wouldn't go that thick. 2-3 inches. So to hold it together, and that was the way we bound all that. And I guess then if you have large bundles, we of course wrap it up with string. Yeah. So that was sort of the last of the high-speed printers. Although I guess actually, although it's past this era, we did have a set of IBMs after kind of the era we're talking about.
2009.
So that's kind of the era up to the mid '70s at Livermore. Amazing run of unique things which are still around like sludgy devices.
Dave, one of the other strange ways of putting it together, we also did the experiment with a string thing that wrapped it in 2 directions, that the cut paper over, because the gluer was always locked up.
Yes, glue. Or it didn't catch some of
it. They had a device that would it would literally wrap the string in 2 directions around a bundle of paper because you couldn't glue it.
Or like in a bakery.
Yeah, like a bakery, except the machine did this thing.
Also, when they were glued, they had to put the stack into a shaker to get them very well aligned, because if you dip the backing into the glue bath and they weren't aligned, of course half your pages would fall out, and that wasn't so great either. That's sort of what we had planned, but maybe we should take questions for a couple more minutes.
What about the engineer's tombstone, the paging segmentation?
Well, that was, didn't John talk about that in January? Did John talk about that in January?
Well,
Nobody knows what that is.
Oh, okay.
We built the thing.
We have there's a question back, and then I'll talk about the paging systems, please.
How did the lark play music?
It was just the frequency of how often a bit was turned on or off. And so you selected certain bits to portray different sounds, and it was the frequency of how often you turned it on.
They just put a speaker on one of the flip-flops. But one of the things the operators used to do in the early days was we hooked up a speaker to a couple of bits on one of the main registers, and you could tell if the machine was running normally by whether the noise, the music, was the audio tones were, had an appropriate randomness to them. And if the thing would get locked into a loop, also you'd hear a repetitive sound replaying, you know that the thing had locked up, and so that the operator would know to go pay some attention to the machine. So sound was a very important feedback mechanism on the early machines.
Further comments? Sure.
Well, I was good.
I got something I want to say at the end.
Okay, but I promise to say just a word about the paging system. George is on. The early PDP-6, the 2 PDP-6s that we had at the time just a single relocation register, which limited the kinds of things you could do and some of the early, when we were trying to put some of the early time-sharing systems. So in the same era, some of you remember that the Multics project was going, and one of the systems they built was a GB645, or worked in the process of building was a GB645, which had a very sophisticated paging and segmenting system on it. And that looked pretty fancy to us, so we said, well, if good enough for them, we need one in Livermore. So we actually, one of my projects early on was to hand build, we actually built this paging and segmenting system for the PDP-6, which actually worked. Although the PDP-6s were subsequently replaced by the PDP-10s, which had a pair of relocation registers, which allowed you to accomplish most of the things that the segmenting concepts with the second relocation register, so we never went back and put the paging system on it. And I guess an anecdote there, that was our first real use of integrated circuits. TPL had just become available. TPL ICs, small scale ICs. And they're basically used, they're military grade components. And we implemented much of this paging system using that logic by running it offset. There was a 0 to 5 volt logic, and whereas the deck logic was 0 to +3, we actually ran that stuff off ground. I think it was -170 to +33 or some weird number like that, and directly coupled it into the chip logic or the deck logic. It was really over, but it worked. It was great. Let's see. So with that, that's probably one of the crazier things we did for this one. Maybe Ed had a parting comment.
Anybody else want to make a parting comment?
Hans. That's great.
Hans?
I don't really mention anything about the going through memory. On the 701, we operated the machine for about 3 or 4 months, and occasionally the memory would go to all ones. And then one day we found out that the memory was facing the double door on the side. And we opened the double door, the sun would hit the memory, and that was it.
I don't know if all of you heard Hans's comment, but it was basically that when the 701 was here with the Williams tube memory, periodically the memory would essentially disappear. And the reason for that was that when they oriented the machine, they oriented facing south, and there was a nice big double door there, so when the sun shone through, the memory disappeared. It took a while to figure out what was going on. Chuck, you have something you want to add?
Well, I just want to say thank you for the opportunity to sit up here in front and make fools of ourselves. We enjoyed it. We've been doing that well for 30 or more years. And so, I don't. I would also like to make one other comment, though, and there's no such thing as the good old days.
Let's see, I guess I'd like to again recognize the real contributions that Fernbach made in enabling us to do all these things. He was an amazing man that allowed a bunch of engineers like us to go off and do some pretty wild things. I think probably there were very few places that had the environment where we could have gone off and tried such interesting things and done some very pioneering work. I just feel very lucky and fortunate to have been a part of it. So thank you.
I too want to say thanks to all of you for coming and listening to us old guys talk about the good old days. It would be nice to be young again, but that's not possible. I want to thank George Michael for contacting me and getting this thing going. I'd like to pay special recognition to a person that is here tonight that I mentioned earlier, who has mentored us and watched over us for years and years. She remembers all our birthdays. She remembers all our children. She was here in the beginning. She has the affectionate term of Mother Hen, but basically we all love you. Cecilia, thanks. Has been up here with us, but she politely refused and full rank, so what can we say? Thank you very much.
Thank you.